Black holes are often painted as the universe's ultimate, void's dark, destructive forces that devour everything in their path. But what if they're more than just cosmic vacuums? What if they're gateways whispering secrets about the very fabric of reality? Imagine them as cosmic Rosetta Stones, holding the key to decoding the universe's hidden language. These enigmatic giants don't just consume light, they cast shadows that reveal the unseen, bending space-time and gravity in ways that challenge our understanding of existence itself. What do these shadows tell us? How do black holes act as portals to realms beyond our comprehension? In this journey, we'll dive into the science, the theories, and the awe-inspiring phenomena that make black holes not just mysteries, but messengers of the cosmos. Together, we'll explore how their shadows and portals might just hold the answers to some of the universe's deepest questions. Picture this, a boundary in space so powerful that not even light can escape its grasp. This is the event horizon of a black hole, the point of no return where the universe seems to bend its own rules. It's here, at this invisible edge, that black holes reveal their first mystery, a place where gravity becomes so intense that it traps everything, even the fastest thing in existence. But black holes aren't just cosmic traps, they're born from the dramatic collapse of massive stars, transforming into objects so dense that their gravitational pull reshapes the very fabric of space and time. When a star exhausts its fuel, it can no longer withstand the crushing force of its own gravity. In a spectacular finale, it implodes, giving birth to a black hole, a region where matter is compressed into an infinitely small point called a singularity. This singularity is a paradox, a place where the laws of physics as we know them break down. Yet, despite their seemingly destructive nature, black holes play a crucial role in the universe. They act as cosmic architects, influencing the formation and evolution of galaxies. Their immense gravity can dictate the movement of stars and even shape the structure of entire galactic clusters. But what makes black holes truly enigmatic is their ability to warp spacetime itself. Imagine space as a stretchy fabric. A black hole is like a weight so heavy that it creates a deep, inescapable well in that fabric, bending the paths of light and matter around it. This distortion isn't just theoretical, it's been observed, giving us tangible proof of Einstein's theory of general relativity in action. Yet for all we've learned, black holes remain full of unanswered questions. What lies beyond the event horizon? How do they manage to hold the universe's deepest secrets within their shadows? As we peel back the layers of these cosmic mysteries, we begin to see black holes not just as destructive forces, but as gateways to understanding the universe itself. Their shadows and warped realities might just be the clues we need to unlock the hidden language of existence. And as we venture deeper, we'll explore how these enigmatic giants are more than just voids, they're portals to the unknown, challenging us to rethink everything we thought we knew about the cosmos. At the heart of a black hole lies something even more mysterious than its event horizon: the shadow. This isn't just an absence of light, it's a cosmic fingerprint, a unique signature that tells a story about the black hole's shape, size, and even its spin. When we talk about a black hole's shadow, we're not referring to darkness in the traditional sense. Instead, it's a region where the black hole's gravity is so overwhelming that it bends light around itself, creating a silhouette against the glowing backdrop of surrounding matter. This shadow isn't a simple void. It's a complex, dynamic phenomenon that holds clues to the black hole's inner workings. In April 2019, humanity caught its first real glimpse of this shadow. The Event Horizon Telescope, a global network of radio telescopes, unveiled an image of the supermassive black hole at the center of the galaxy Messier 87. This historic image showed a glowing ring of light encircling a dark void, a direct visual representation of the black hole's shadow. What made this image so groundbreaking wasn't just its beauty, but the wealth of information it provided. The size and shape of the shadow confirmed predictions made by Einstein's theory of general relativity, offering a new way to test our understanding of gravity on cosmic scales. It was as if the universe itself had handed us a key to unlocking one of its most profound secrets. But the shadow isn't just a scientific curiosity, it might also be a form of cosmic communication. The way light bends and twists around a black hole creates intricate patterns within the shadow, patterns that could reveal details about the black hole's environment, like the presence of magnetic fields or the behavior of matter spiraling into its depths. Some scientists even speculate that these shadows could act as a kind of universal Rosetta Stone, encoding information about the fundamental laws of physics in their intricate designs. If we can learn to decode these patterns, we might uncover new insights into the nature of spacetime itself. What's truly fascinating is that black hole shadows aren't static. They change over time, influenced by the black hole's activity and the swirling chaos of the material around it. This dynamic nature makes them not just snapshots, but living, breathing records of the black hole's life. And as we continue to study them, we're beginning to realize that these shadows might not just be windows into black holes. They could be gateways to understanding the universe on a deeper level. So, as we peer into these dark regions, we're not just observing the absence of light, we're uncovering the hidden language of the cosmos itself. What if black holes aren't just cosmic vacuums or cosmic architects? What if they're something even more extraordinary? What if they're portals, gateways to other dimensions, or even entirely different universes? This idea might sound like science fiction, but it's rooted in some of the most intriguing theories in modern physics. Black holes, with their mind-bending ability to warp spacetime, could be the key to unlocking pathways to realms beyond our own. And at the heart of this idea lies the concept of wormholes, hypothetical tunnels through spacetime that could connect distant points in the universe, or even bridge entirely separate realities. Let's break this down. A wormhole, often called an Einstein-Rosen bridge, is a theoretical passage through the fabric of spacetime. Imagine folding a piece of paper so that two distant points touch. This is essentially how a wormhole works. It's a shortcut, a cosmic tunnel that could, in theory, allow travel across vast distances in an instant. But here's where it gets even more fascinating. Some scientists speculate that black holes could be the entrances to these wormholes. The intense gravitational forces near a black hole's singularity might create the conditions needed for such a tunnel to exist, bending spacetime so dramatically that it forms a bridge to another location, or even another universe. The idea of traversable wormholes, ones that humans or spacecraft could theoretically pass through, is both thrilling and fraught with challenges. For one, the energy required to keep a wormhole stable is mind-boggling. According to current physics, wormholes would collapse almost instantly unless held open by something called exotic matter, a hypothetical substance with negative energy density. This exotic matter would counteract the immense gravitational forces trying to crush the wormhole shut, but it's something we've yet to discover or create. Even if we could stabilize a wormhole, navigating through it would be no simple feat. The extreme tidal forces near a black hole's singularity would stretch and compress anything passing through in ways that are, quite frankly, unimaginable. Yet, despite these challenges, the idea of black holes as portals remains a tantalizing possibility. Could they be the cosmic doorways that science fiction often dreams of? Or are they simply theoretical constructs, fascinating to ponder but forever out of reach? The truth is, we don't know yet. What we do know is that black holes continue to challenge our understanding of the universe, pushing the boundaries of what we thought was possible. Whether they are gateways to other dimensions or simply the universe's most enigmatic objects, one thing is certain: black holes are far more than just voids in space. They're invitations to explore the unknown, to question the very nature of reality, and to dream of what might lie beyond the limits of our understanding. So, as we ponder the possibility of black holes as portals, we're left with a question that's as profound as it is simple. Are these cosmic gateways real, or are they just a product of our imagination? The answer, much like the black holes themselves, remains shrouded in mystery. But one thing is clear: every step we take toward understanding these cosmic enigmas brings us closer to unraveling the universe's deepest secrets. Gravity is the quiet force that keeps our feet on the ground and the planets in orbit. Yet in the presence of a black hole, it transforms into something far more extraordinary. It's the weakest of the four fundamental forces, but within the realm of black holes, it becomes the ultimate ruler, bending the rules of reality itself. This is where Einstein's theory of general relativity takes center stage, revealing how gravity isn't just a force, it's the curvature of spacetime itself. According to Einstein, massive objects like stars and planets warp the fabric of spacetime around them, much like a bowling ball would dent a soft mattress. But when a black hole enters the picture, this warping becomes extreme, creating a gravitational pull so intense that not even light can escape its grasp. Einstein's equations predicted the existence of black holes long before we had the technology to observe them. He showed that when a massive star collapses under its own gravity, it can create a region of space-time so profoundly curved that it forms a singularity, a point where density becomes infinite and the laws of physics as we know them cease to function. This is the heart of a black hole, where gravity reigns supreme and spacetime itself seems to unravel. But what makes this gravitational dominance even more fascinating is how it shapes the environment around a black hole, creating phenomena like the event horizon and the shadow we've come to associate with these cosmic enigmas. The warping of spacetime around a black hole doesn't just trap light, it bends it, creating the bizarre optical effects we observe. Light traveling near a black hole doesn't follow a straight path. Instead, it spirals around the intense gravitational well, creating the glowing ring we see in images like the one captured by the Event Horizon Telescope. This bending of light isn't just a visual spectacle, it's a direct manifestation of how gravity distorts spacetime. And within this distortion lies the key to understanding black hole shadows. The shadow isn't just a dark spot. It's a region where gravity has twisted spacetime so severely that light can no longer reach us, creating a silhouette against the backdrop of swirling matter. What's remarkable is that the same gravity responsible for creating black holes might also hold the key to unlocking their secrets. By studying how gravity warps light and spacetime, scientists can infer details about a black hole's mass, spin, and even the environment around it. This gravitational lensing effect acts as a cosmic magnifying glass, allowing us to peer deeper into the mysteries of these objects than ever before. And as we continue to explore, we're beginning to see gravity not just as a force, but as a storyteller, one that reveals the hidden language of black holes through the subtle distortions it creates. So, as we unravel the role of gravity in shaping black holes, we're left with a profound realization. These cosmic giants aren't just products of gravity, they're its ultimate expression. And in their shadows, we might just find the clues we need to decode the universe's most enigmatic messages. The event horizon is where the black hole's true power becomes undeniable, a boundary so extreme that it marks the ultimate point of no return. Think of it as a cosmic checkpoint, a line in the fabric of spacetime where the rules of the universe shift dramatically. Once something crosses this threshold, whether it's a beam of light or a wayward star, there's no coming back. This invisible edge is what defines a black hole, separating the known universe from the incomprehensible mysteries that lie within. It's not just a physical boundary, it's a cosmic threshold, a place where the familiar laws of physics begin to unravel. But what happens as objects approach this boundary? Imagine a spacecraft venturing too close to a black hole. As it nears the event horizon, the gravitational pull becomes so intense that the force on the side closest to the black hole is vastly stronger than the force on the far side. This difference in gravity stretches the spacecraft into a long, thin strand, a process scientists call spaghettification. It's as if the black hole is pulling on the object like taffy, stretching it until it's torn apart. This isn't just theoretical, it's a real phenomenon that underscores the sheer power of black holes. Even light, the fastest thing in the universe, isn't immune to this fate. Once it crosses the event horizon, it's trapped forever, adding to the black hole's shadowy silhouette. Yet, for all its destructive reputation, the event horizon might hold more secrets than we realize. Some theories suggest it's not just a one-way street. While nothing can escape once it crosses this boundary, the event horizon itself might be a dynamic, ever-changing surface, a place where quantum effects and gravity collide in ways we're only beginning to understand. Could it be a kind of cosmic firewall, a region of intense energy where matter is transformed into something entirely new? Or is it a gateway to deeper truths about the nature of spacetime itself? As we probe deeper into the mysteries of the event horizon, we're left with more questions than answers. But one thing is certain, this boundary isn't just a line in the sand. It's a window into the strange, mind-bending physics that govern the most extreme environments in the universe. And as we continue to explore, we might just find that the event horizon is more than a point of no return. It's a starting point for understanding the cosmos in ways we've never imagined. Black holes have long been thought of as the ultimate cosmic devourers, consuming everything in their path and leaving nothing behind. But in the 1970s, Stephen Hawking turned this idea on its head with a groundbreaking discovery. Black holes aren't completely black. They emit something called Hawking radiation, a faint glow of energy that slowly leaks out over time. This revelation wasn't just a scientific breakthrough, it was a moment that reshaped our understanding of black holes and the universe itself. So, how does this work? At the heart of Hawking radiation lies the strange and counterintuitive world of quantum mechanics. In the quantum realm, empty space isn't truly empty. Instead, it's a bubbling sea of particles and antiparticles that constantly pop into existence and annihilate each other. Near the event horizon of a black hole, however, things get interesting. Sometimes one of these particles falls into the black hole while the other escapes, carrying energy away. Over time, this process siphons energy from the black hole, causing it to slowly evaporate. It's as if the black hole is leaking one particle at a time. This intersection of quantum mechanics and general relativity is what makes Hawking radiation so fascinating and so challenging. Einstein's theory of gravity describes the immense pull of black holes, while quantum mechanics explains the bizarre behavior of particles at the tiniest scales. Hawking's insight was to bridge these two worlds, showing that even the most extreme environments in the universe are governed by the rules of the quantum realm. But this discovery also raised a profound question. If black holes can evaporate, what happens to all the information they've swallowed? The idea of information loss in black holes has become one of the biggest puzzles in modern physics. According to quantum mechanics, information about the state of particles can't simply vanish, it's preserved, even if it's scrambled beyond recognition. But if a black hole evaporates completely, what happens to the information it once contained? Does it disappear forever, violating the principles of quantum physics? Or is there a way for it to escape, perhaps encoded in the Hawking radiation itself? This question, known as the information paradox, remains one of the most hotly debated topics in science today. Hawking radiation doesn't just challenge our understanding of black holes, it also has profound implications for their lifespan. For supermassive black holes, which can weigh billions of times more than our Sun, the process of evaporation is so slow that it would take trillions of years to make a noticeable difference. But for smaller black holes, the story is different. A black hole with the mass of a small mountain could evaporate in less than the age of the universe, ending its life in a burst of energy. This raises the tantalizing possibility of detecting these final moments, offering a glimpse into the ultimate fate of black holes. As we grapple with the mysteries of Hawking radiation, we're reminded that black holes are far more dynamic than we once thought. They're not just eternal voids, they're cosmic entities with a life cycle, slowly fading away over unimaginable timescales. And in their fading, they might just hold the key to understanding some of the deepest questions in physics. What happens to the information they consume? How does the quantum world interact with gravity? These are the questions that drive us forward, pushing the boundaries of what we know and challenging us to rethink the very nature of reality. Hawking radiation isn't just a scientific curiosity, it's a window into the hidden connections that shape our universe. And as we continue to explore its implications, we're left with a sense of wonder. What other secrets might black holes hold waiting to be uncovered? Imagine throwing a book into a fire. The pages burn, the ink fades, but the information, the story, the ideas aren't truly lost. They're transformed into heat, light, and ash, still traceable in some form. But what if you threw that book into a black hole? According to our current understanding of physics, the information in that book might vanish forever. This is the essence of the black hole information paradox, a puzzle that pits two of science's greatest theories against each other: quantum mechanics and general relativity. At its core, the paradox revolves around a simple yet profound question. What happens to information that falls into a black hole? Quantum mechanics, the framework that governs the behavior of particles at the smallest scales, insists that information can never be destroyed. It might change form, but it's always conserved. General relativity, on the other hand, paints a different picture. When matter crosses a black hole's event horizon, it's crushed into the singularity, where the laws of physics as we know them break down. From this perspective, the information seems to vanish without a trace. How can these two theories, both incredibly successful in their own domains, be so fundamentally at odds? Enter the holographic principle, a radical idea that might hold the key to resolving this paradox. This principle suggests that all the information swallowed by a black hole isn't lost. It's encoded on the event horizon, the black hole's outer boundary. Imagine the event horizon as a kind of cosmic hard drive, storing data in 2 dimensions rather than 3. In this view, the information isn't destroyed. It's simply translated into a different format, like a 3-dimensional image being compressed into a 2-dimensional hologram. This idea not only challenges our understanding of black holes, but also redefines how we think about space-time itself. The holographic principle isn't just a theoretical exercise, it's supported by some fascinating mathematics. Physicists have shown that the entropy or disorder of a black hole is proportional to the area of its event horizon, not its volume. This finding aligns with the idea that information is stored on the surface, not within the black hole itself. It's as if the universe has a built-in backup system, ensuring that nothing is ever truly lost, no matter how extreme the conditions. But the holographic principle isn't the only theory attempting to solve the information paradox. Some researchers propose that black holes might have soft hair, subtle quantum features on their event horizons that encode the information of what falls in. Others suggest that information could escape through Hawking radiation, the faint glow of energy black holes emit over time. While these ideas are still speculative, they highlight the creativity and determination of scientists working to unravel this cosmic conundrum. The black hole information paradox isn't just a technical debate, it's a window into the deepest questions about the nature of reality. How does information persist in a universe governed by both quantum mechanics and gravity? What does it mean for something to truly disappear? These questions push us to rethink our assumptions and explore new frontiers in physics. And as we continue to probe the mysteries of black holes, we might just find that the answers lie not in the darkness of their interiors, but in the light of their boundaries where the universe itself might be leaving clues for us to decode. The holographic principle is one of those ideas that sounds like it belongs in the realm of science fiction, yet it's grounded in some of the most cutting-edge science of our time. At its core, this principle suggests that the universe might not work the way we've always imagined. Instead of information being spread out across three-dimensional space, it could be encoded on a two-dimensional surface. Think of it like a cosmic hologram where every detail of a three-dimensional object is stored on a flat plane. When applied to black holes, this idea becomes even more mind-bending. It proposes that all the information swallowed by a black hole isn't lost within its depths. It's projected onto its event horizon, the black hole's outer boundary. This concept bridges two of physics' greatest theories, quantum mechanics and general relativity. Quantum mechanics deals with the behavior of particles at the smallest scales, while general relativity explains the large-scale structure of spacetime and gravity. For decades, these two frameworks have been at odds, especially when it comes to black holes. But the holographic principle offers a potential way to reconcile them, suggesting that the information about everything that falls into a black hole is preserved on its surface, not destroyed within its singularity. The implications of this idea are staggering. If the holographic principle is correct, it means that the universe itself could be a kind of hologram. Just as a two-dimensional holographic image can create the illusion of depth, the information encoded on the event horizon of a black hole might hold the key to understanding the three-dimensional reality we experience. This isn't just a philosophical musing. It's a mathematical framework that has been explored by some of the brightest minds in physics. But how does this connect to what we see when we observe black holes? Remember the shadows we've been discussing, those dark silhouettes surrounded by glowing rings of light. The holographic principle suggests that these shadows might not just be empty voids. Instead, they could be intricate patterns encoding information about the black hole's history, its contents, and even the fundamental laws of physics. It's as if the black hole is projecting a kind of cosmic cinema, with its shadow acting as the screen. What's truly fascinating is that this principle doesn't just apply to black holes. It could reshape our understanding of the entire universe. If the holographic principle holds, it means that the information required to describe our three-dimensional reality could, in theory, be stored on a two-dimensional surface at the boundary of the cosmos. This idea challenges our intuitive sense of space and time, suggesting that the universe might be far more interconnected than we ever imagined. As we explore the holographic principle, we're not just uncovering the secrets of black holes, we're peering into a new way of understanding reality itself. Could the universe really be a hologram? Are black holes the key to unlocking this cosmic code? These questions push the boundaries of science and imagination, inviting us to see the universe in a way that's as beautiful as it is profound. And as we continue to unravel these mysteries, we might just find that the answers lie not in the depths of black holes, but on their surfaces where the universe writes its story in the language of light and shadow. At the very heart of a black hole lies the singularity, a point where the universe seems to throw up its hands and say, "I give up." Here, in this unimaginably small, infinitely dense core, the laws of physics as we know them break down completely. Gravity becomes so overwhelming that space-time itself is crushed into a point of zero volume, where density becomes infinite. It's a place where the rules of the universe no longer apply, and our most trusted theories, general relativity and quantum mechanics, reach their limits. The singularity is the ultimate mystery, a cosmic question mark that challenges everything we think we know about reality. But what does it mean for physics to break down? Imagine trying to use a map that only works in flat terrain when you're climbing a mountain. At some point, the map becomes useless. It doesn't account for the steep slopes or the jagged cliffs. In the same way, our current understanding of physics works beautifully in most of the universe, but at the singularity, it collapses. General relativity, which describes gravity and the curvature of space-time, predicts that the singularity exists, but it can't tell us what happens there. Quantum mechanics, which governs the behavior of particles at the smallest scales, offers clues but doesn't fully explain the extreme conditions of the singularity. It's as if the universe is hiding its deepest secrets behind a veil we're not yet equipped to pierce. This is where the quest for quantum gravity comes in. Quantum gravity is the theoretical framework that aims to unite general relativity and quantum mechanics, two pillars of modern physics that are currently at odds. If we can find a way to merge these theories, we might finally understand what happens at the singularity. Some scientists propose that quantum gravity could reveal a universe where singularities don't exist as we imagine them. Instead, they might be replaced by something entirely new, like a quantum foam or a fuzzy, fluctuating region where spacetime behaves in ways we can't yet comprehend. The singularity also raises a profound question. Is it a real physical phenomenon, or is it just a mathematical artifact, a sign that our equations are incomplete? Some researchers argue that singularities are simply the result of pushing our current theories too far, like asking a calculator to divide by zero. In this view, the singularity might not be a place of infinite density, but rather a signal that we need a better understanding of the universe's most extreme environments. As we grapple with the enigma of the singularity, we're reminded that black holes aren't just cosmic oddities, they're laboratories for testing the limits of human knowledge. They challenge us to rethink our assumptions, to question the very foundations of physics, and to imagine new possibilities. The singularity might be where physics breaks down, but it's also where our curiosity is reignited, driving us to explore the unknown and uncover the universe's deepest truths. So, is the singularity real, or is it just a mathematical construct? The answer lies somewhere in the uncharted territory between our current understanding and the breakthroughs yet to come. And as we venture into that territory, we're not just seeking answers, we're rewriting the story of the cosmos itself. Black holes are often seen as cosmic destroyers, but what if they're also cosmic creators? Far from being just voids in space, black holes, especially supermassive ones, play a pivotal role in shaping the very galaxies that surround them. These colossal giants, often found at the heart of galaxies, aren't just passive inhabitants, they're active participants in the grand dance of the universe. Their immense gravitational pull and energetic outbursts influence everything from star formation to the large-scale structure of the cosmos. In many ways, black holes aren't just part of galaxies, they're the architects behind them. Take, for example, the supermassive black hole at the center of our own Milky Way, known as Sagittarius, a star. While it might seem like a quiet giant today, its presence has profoundly shaped the galaxy we call home. Black holes like this one don't just sit idly by, they interact with their surroundings in ways that are both subtle and dramatic. One of their most significant roles is regulating star formation. When a black hole feeds on surrounding gas and dust, it doesn't just consume, it also releases enormous amounts of energy in the form of jets and radiation. These outbursts can heat up nearby gas, preventing it from collapsing into new stars. In this way, black holes act as cosmic regulators, controlling the rate at which stars are born and ensuring that galaxies don't burn out too quickly. But their influence doesn't stop there. Black holes also play a key role in shaping the structure of galaxies themselves. The powerful jets emitted by supermassive black holes can push gas and dust outward, creating vast bubbles that stretch across thousands of light years. These bubbles not only clear out regions of space, but also trigger the formation of new stars in their wake. It's a delicate balance. While black holes can suppress star formation in their immediate vicinity, their energetic activity can also spark new stellar birth in more distant regions. This dynamic interplay between creation and destruction is what makes black holes so essential to the life cycle of galaxies. What's even more fascinating is the symbiotic relationship between black holes and their host galaxies. Studies have shown that the size of a galaxy's central black hole is closely linked to the galaxy's overall structure. Larger galaxies tend to have larger black holes, suggesting that the two grow and evolve together. This connection hints at a deeper cosmic partnership, where black holes and galaxies influence each other's development over billions of years. It's as if black holes are the unseen hands guiding the growth of the galaxies they inhabit. As we look out into the universe, we begin to see black holes not just as isolated phenomena, but as integral parts of a much larger cosmic story. They're not just shaping galaxies, they're shaping the universe itself. From regulating star formation to sculpting the large-scale structure of the cosmos, black holes are the unseen architects of the universe's grand design. And as we continue to explore their mysteries, we're left with a profound realization. Black holes aren't just the universe's most enigmatic objects, they're its most essential builders. This intricate dance between black holes and galaxies raises a question that echoes through the cosmos. Are black holes the architects of the universe, or are they simply one piece of a much larger puzzle? The answer, much like the black holes themselves, remains shrouded in mystery. But one thing is certain: their role in shaping the cosmos is as profound as it is fascinating. And as we peer deeper into the universe, we're reminded that black holes aren't just voids, they're the silent forces that shape the stars, the galaxies, and the very fabric of existence. Supermassive black holes are the titans of the cosmos, lurking at the heart of nearly every galaxy, including our own Milky Way. Unlike their smaller stellar mass counterparts, these giants can weigh millions or even billions of times the mass of our Sun. But how do they grow so massive, and what role do they play in shaping the galaxies they inhabit? These questions lie at the heart of one of the universe's greatest mysteries. The formation of supermassive black holes is still a puzzle scientists are working to solve. One leading theory suggests they began as smaller black holes, formed from the collapse of massive stars in the early universe. Over billions of years, these black holes grew by devouring gas, dust, and even other black holes, merging in a cosmic feeding frenzy. Another intriguing possibility is that supermassive black holes formed directly from the collapse of enormous clouds of gas in the early universe, bypassing the star stage altogether. Whatever their origins, these colossal objects have had billions of years to grow, shaping the galaxies around them in the process. But supermassive black holes aren't just massive, they're also incredibly active. When they feed on surrounding material, they don't do so quietly. The infalling gas heats up and spirals into the black hole at nearly the speed of light, releasing tremendous amounts of energy. This process powers some of the brightest objects in the universe, quasars and active galactic nuclei. Quasars, in particular, are so luminous that they can outshine entire galaxies, even from billions of light years away. These dazzling beacons are essentially supermassive black holes in action, their brilliance fueled by the frenetic energy of their feeding. The influence of supermassive black holes extends far beyond their immediate surroundings. Their jets and radiation can heat up interstellar gas, preventing it from collapsing into new stars. In this way, they act as cosmic regulators, controlling the rate of star formation in their host galaxies. At the same time, the energy they release can trigger star formation in more distant regions, creating a delicate balance between creation and destruction. It's a dynamic interplay that shapes the evolution of galaxies over billions of years. What's truly remarkable is the connection between supermassive black holes and their host galaxies. Studies have shown that the size of a galaxy's central black hole is closely tied to the galaxy's overall structure. Larger galaxies tend to have larger black holes, suggesting that the two grow and evolve together. This relationship hints at a deeper cosmic partnership, where black holes and galaxies influence each other's development in ways we're only beginning to understand. So, what does this mean for the universe as a whole? Supermassive black holes are more than just galactic anchors, they're cosmic engines, driving the evolution of galaxies and shaping the large-scale structure of the cosmos. From powering quasars to regulating star formation, their influence is both profound and far-reaching. As we continue to study these enigmatic giants, we're left with a question that echoes through the cosmos. Are supermassive black holes the architects of the universe, or are they simply one piece of a much larger puzzle? The answer, much like the black holes themselves, remains shrouded in mystery. But one thing is certain, their role in shaping the cosmos is as fascinating as it is essential. Now let's step into the cosmic ballet of binary black holes, a phenomenon so extraordinary that it stretches our understanding of gravity and space-time to its limits. Picture two black holes, each with a mass of dozens or even hundreds of suns, locked in a gravitational dance. They circle each other, spiraling closer and closer over millions or even billions of years, until finally they collide in a cataclysmic merger. This isn't just a rare cosmic event, it's a spectacle that sends ripples through the very fabric of the universe. Binary black holes form in a variety of ways. Sometimes they originate from pairs of massive stars that collapse into black holes, remaining bound together by their shared gravity. Other times, black holes in dense star clusters can find each other, drawn together by chance encounters. However they form, these duos are bound by an unbreakable gravitational bond, orbiting one another in a slow, inevitable spiral. But what makes this dance so fascinating isn't just the black holes themselves, it's the energy they release as they merge. When two black holes collide, they don't just come together quietly. The merger unleashes an incredible burst of energy in the form of gravitational waves, ripples in space-time predicted by Einstein over a century ago. These waves aren't like sound or light. They're distortions in the very fabric of the universe, propagating outward at the speed of light. The first detection of gravitational waves in 2015 by the LIGO Observatory was a monumental moment in science, confirming Einstein's predictions and opening a new window into the cosmos. Since then, dozens of binary black hole collisions have been observed, each one offering new insights into the nature of gravity and black holes. What's truly remarkable about these collisions is how they test the limits of our understanding. Einstein's theory of general relativity predicts how black holes should behave as they spiral together and merge, and so far, every observation has matched those predictions with astonishing precision. But scientists are always on the lookout for discrepancies, tiny deviations that could hint at new physics beyond Einstein's framework. Binary black holes are, in a sense, cosmic laboratories, allowing us to probe the fundamental laws of the universe in ways that were once unimaginable. The gravitational waves produced by these mergers don't just confirm Einstein's theories, they also reveal the properties of the black holes themselves. By analyzing the waves, scientists can determine the masses of the black holes, their spins, and even the orientation of their orbits. It's like listening to the universe's symphony, where each collision plays a unique note, telling us a story about the black holes involved. And as we detect more of these events, we're building a richer picture of how black holes form, evolve, and shape the cosmos. But the story doesn't end with the collision. When two black holes merge, they create a single, more massive black hole, often spinning rapidly like a cosmic top. This newly formed black hole can continue to influence its surroundings, shaping the galaxy it resides in and potentially triggering new waves of star formation. And the gravitational waves it produces, they travel across the universe, carrying with them the echoes of this incredible event. As we listen to these cosmic ripples, we're reminded that binary black holes aren't just isolated phenomena, they're part of a larger, interconnected universe. Their collisions are like cosmic drumbeats, reverberating through space-time and offering us a glimpse into the deepest mysteries of existence. And with each new detection, we're not just observing the universe, we're hearing its story, one gravitational wave at a time. So, as we marvel at the dance of binary black holes, we're left with a question that resonates far beyond the confines of our understanding. What other secrets might these gravitational ripples reveal about the universe? The answer lies in the waves, waiting to be decoded by the curious minds of scientists and perhaps by the next generation of cosmic listeners. Gravitational waves are the universe's way of whispering its secrets to us, ripples in the fabric of spacetime itself, created by some of the most violent and energetic events in the cosmos. Imagine throwing a pebble into a still pond and watching the waves spread outward. Now replace the pebble with two colliding black holes and the pond with the fabric of reality. The result, gravitational waves, ripples that carry the echoes of these cataclysmic events across the universe. These waves aren't just a curiosity, they're a revolutionary tool, allowing us to listen to black holes in ways we never thought possible. The story of gravitational waves begins with Albert Einstein, who predicted their existence over a century ago as part of his theory of general relativity. He theorized that massive objects like black holes or neutron stars could warp spacetime so dramatically that they'd send out ripples as they move. But detecting these ripples seemed like an impossible task. After all, they're incredibly faint by the time they reach Earth, requiring instruments of almost unimaginable precision to pick them up. That's where LIGO, the Laser Interferometer Gravitational Wave Observatory, comes in. In 2015, LIGO made history by detecting gravitational waves for the first time, confirming Einstein's prediction and opening a new window into the universe. What LIGO detected wasn't just a faint ripple, it was the unmistakable signature of two black holes colliding. As these massive objects spiraled toward each other, they distorted spacetime, sending out waves that traveled over 1 billion light years before reaching Earth. The signal, often described as a chirp, lasted just a fraction of a second, but it carried a wealth of information. From this brief sound, scientists could determine the masses of the black holes, their spins, and even the energy released during the collision. It was like hearing the universe's heartbeat for the first time, a moment that changed astronomy forever. Since that first detection, LIGO and its sister observatories have picked up dozens of gravitational wave signals, each one telling a unique story about the cosmos. These waves have revealed not just black hole collisions, but also mergers of neutron stars, offering insights into everything from the origin of heavy elements to the expansion rate of the universe. But perhaps the most exciting aspect of gravitational waves is how they allow us to listen to black holes. Unlike light, which can be blocked or absorbed, gravitational waves pass through everything, carrying information from the most extreme environments in the universe. It's as if black holes are speaking to us in a language we're only beginning to understand. What's truly fascinating is how these waves might help us unravel the mysteries of black hole shadows. Gravitational waves don't just tell us about the black holes themselves, they also reveal the intricate dance of spacetime around them. By studying the waves produced during mergers, scientists can infer details about the black hole's event horizons and the regions just outside them. This information could provide new clues about the shadows black holes cast, helping us decode the complex interplay of light, gravity, and spacetime. In a sense, gravitational waves might be the key to translating the hidden language of black holes, turning their whispers into a cosmic symphony. As we continue to listen to the universe through gravitational waves, we're reminded that black holes aren't just silent giants lurking in the darkness. They're dynamic, energetic objects that shape the cosmos in ways we're only beginning to comprehend. And with each new detection, we're not just hearing the universe, we're uncovering its deepest secrets, one ripple at a time. The story of black holes is far from over, and gravitational waves are giving us a front-row seat to the cosmic drama unfolding all around us. Black holes have long been the stuff of science fiction, often portrayed as gateways to distant galaxies or even different eras. But could they really be portals to the past or future? The idea of time travel has fascinated humanity for centuries, and black holes, with their mind-bending gravitational effects, might just hold the key to making it a reality, or at least a theoretical possibility. To understand how this could work, we need to dive into the strange world of spacetime and the extreme environments black holes create. At the heart of this idea is Einstein's theory of general relativity, which tells us that gravity isn't just a force, it's the curvature of spacetime itself. Black holes, with their immense gravitational pull, warp spacetime so severely that they create conditions unlike anything else in the universe. One of the most intriguing predictions of general relativity is the existence of closed time-like curves, or CTC. These are paths through spacetime that loop back on themselves, theoretically allowing an object or even a person to travel back in time. Imagine drawing a circle on a piece of paper. A closed time-like curve is like that circle, but in 4 dimensions. It's a loop that connects the past to the future. Near a black hole's intense gravitational field, spacetime could twist in such a way that these loops become possible. But how would this work in practice? Picture a spaceship orbiting a rapidly spinning black hole, known as a Kerr black hole. The extreme rotation of the black hole drags spacetime around with it, creating a phenomenon called frame dragging. This twisting of spacetime could, in theory, form a closed time-like curve, allowing the spaceship to follow a path that loops back to an earlier point in time. It's a mind-boggling concept, one that challenges our understanding of cause and effect. If you could travel back in time, could you change the past? Or would the universe somehow prevent such paradoxes from occurring? This brings us to the thorny issue of causality, the principle that cause must always precede effect. Time travel through closed time-like curves could potentially violate this fundamental rule, leading to paradoxes like the famous grandfather paradox, where a time traveler prevents their own existence by altering the past. Some physicists argue that nature might enforce chronology protection, a kind of cosmic rule that prevents time travel from happening. Others suggest that the universe could find ways to resolve these paradoxes, perhaps through the mysterious workings of quantum mechanics. While these ideas remain speculative, they highlight the profound questions black holes raise about the nature of time itself. So, is time travel through black holes possible, or is it just the stuff of science fiction? The truth is, we don't yet have the answers. While the mathematics of general relativity allows for the possibility of closed time-like curves, the practical challenges are immense. The energy required to create and stabilize such a path would be beyond anything we can currently imagine, and the extreme conditions near a black hole's event horizon would make any attempt at time travel incredibly dangerous. But even if time travel remains out of reach, the theories surrounding it push the boundaries of our understanding, challenging us to think in new ways about the universe and our place within it. As we explore these ideas, we're reminded that black holes aren't just cosmic oddities, they're windows into the deepest mysteries of existence. Whether they hold the key to time travel or simply inspire us to dream, they continue to captivate our imaginations and drive our quest for knowledge. And as we peer into their depths, we're left with a tantalizing question. If time travel were possible, what would we discover about the universe and about ourselves? The cosmic censorship hypothesis is one of those ideas that sounds like it belongs in a sci-fi thriller, but it's actually a deeply rooted concept in theoretical physics. Proposed by physicist Roger Penrose in the late 1960s, this hypothesis suggests a kind of cosmic rule: singularities, those infinitely dense points at the heart of black holes, are always hidden behind event horizons. In other words, the universe has a built-in mechanism to keep these extreme, physics-breaking regions out of sight. It's as if nature itself is saying, what happens in the singularity stays in the singularity. But why does this matter, and what happens if this rule is broken? At its core, the cosmic censorship hypothesis is about preserving the predictability of the universe. Singularities are places where the laws of physics as we know them break down, and if they were exposed, what scientists call naked singularities, they could wreak havoc on our understanding of cause and effect. Imagine being able to see or interact with a singularity directly. The extreme conditions there could produce effects that defy our current theories, making the universe unpredictable and chaotic. The hypothesis acts as a safeguard, ensuring that singularities remain hidden behind the veil of an event horizon, keeping the universe orderly and governed by the laws we understand. But not everyone is convinced that cosmic censorship is an absolute rule. Some physicists argue that naked singularities could exist under certain conditions, challenging the hypothesis. For instance, in the case of a rapidly spinning black hole, the intense rotation could distort the event horizon in such a way that the singularity becomes exposed. If this were to happen, it would be like lifting the curtain on the universe's most extreme and mysterious phenomenon, offering a glimpse into the unknown. The debate over whether naked singularities are possible is still ongoing, with some researchers exploring mathematical models that allow for their existence, while others argue that nature would never permit such a violation of cosmic order. This debate isn't just an academic exercise, it has profound implications for how we understand black holes and the universe itself. If naked singularities do exist, they could provide a unique window into the nature of spacetime and gravity, offering clues about how to reconcile general relativity with quantum mechanics. On the other hand, if the cosmic censorship hypothesis holds true, it reinforces the idea that the universe operates within certain boundaries, maintaining a balance between chaos and order. And here's where black hole shadows come into play. The shadows we observe around black holes are directly tied to the event horizon, the boundary that hides the singularity from view. If a black hole's shadow were to show irregularities or unexpected features, it could hint at something unusual happening near the event horizon, perhaps even the presence of a naked singularity. This connection makes black hole shadows not just fascinating visual phenomena, but also potential tools for testing the cosmic censorship hypothesis. As we grapple with these ideas, we're reminded that black holes are more than just cosmic curiosities. They're laboratories for exploring the deepest questions about the universe. Whether singularities remain hidden or occasionally peek out from behind their cosmic veil, they challenge us to rethink our understanding of reality. And as we continue to study black hole shadows, we might just find the answers to some of the universe's most profound mysteries. The cosmic censorship hypothesis invites us to consider the delicate balance that governs the cosmos. Are singularities always hidden, or could nature sometimes let its secrets slip? The answer lies somewhere in the shadows, those dark, enigmatic regions that hold the key to understanding the universe's most extreme environments. And as we peer into those shadows, we're left with a question that lingers. What other cosmic rules might black holes reveal, and how will they reshape our understanding of reality? Now, let's turn our attention to one of the most heated debates in modern physics, the firewall paradox. Imagine approaching a black hole's event horizon, expecting to cross into the unknown, only to be met by a blazing wall of fire. This isn't science fiction, it's a real theoretical conundrum that challenges our understanding of black holes and the very fabric of reality. At the heart of this paradox lies a clash between two fundamental theories, quantum mechanics and general relativity. And it's a clash that might just rewrite the rules of the universe as we know them. The firewall paradox emerged in 2012 when a group of physicists proposed a startling idea. The event horizon of a black hole might not be the smooth, uneventful boundary we once thought. Instead, it could be a fiery barrier, a firewall of high-energy particles that would incinerate anything trying to cross it. This idea was born out of an attempt to resolve a long-standing problem in black hole physics, the information paradox. If black holes evaporate over time through Hawking radiation, what happens to the information about the matter they've swallowed? Quantum mechanics insists that information can't be destroyed, but black holes seem to defy this rule. The firewall hypothesis suggests that the information might be preserved at the event horizon, but at a cost, a wall of fire that would destroy anything encountering it. This proposal sent shockwaves through the physics community. For decades, the event horizon was thought to be a relatively gentle place, at least from the perspective of someone falling in. According to Einstein's theory of general relativity, an observer crossing the event horizon wouldn't notice anything unusual. They'd simply pass through, blissfully unaware. But the firewall paradox turns this idea on its head, suggesting that the event horizon is anything but gentle. Instead, it's a place of extreme energy where particles collide with such force that they create a literal wall of fire. This idea not only challenges our understanding of black holes, but also raises profound questions about the nature of spacetime itself. But is the firewall real, or is it just a theoretical construct? Some physicists argue that firewalls are a necessary consequence of quantum mechanics, a way to preserve the integrity of information in the face of black hole evaporation. Others, however, see them as a sign that our current theories are incomplete. If firewalls exist, they would violate the principle of equivalence, a cornerstone of general relativity that states that an observer in free fall shouldn't feel any effects of gravity. This has led some researchers to propose alternative solutions to the paradox, such as the idea that the event horizon might be fuzzy, with quantum effects smoothing out the extreme energy into something less destructive. The debate over firewalls is far from settled, but it highlights the deep connections between black holes and the fundamental laws of physics. Whether or not firewalls exist, they force us to confront the limits of our understanding and to consider new possibilities. Are black holes truly the fiery fortresses the firewall hypothesis suggests, or is there a more elegant solution waiting to be discovered? As we grapple with these questions, we're reminded that black holes aren't just cosmic oddities. They're the ultimate testing grounds for our theories about the universe. So, as we ponder the firewall paradox, we're left with a question that burns as brightly as the firewalls themselves. Are these fiery barriers real, or are they simply a sign that we're missing a piece of the cosmic puzzle? The answer, much like the event horizon, remains shrouded in mystery. But one thing is certain: every step we take toward understanding black holes brings us closer to unraveling the universe's most profound secrets. And in the process, we might just discover that the firewalls aren't the end of the story, but the beginning of a new chapter in our quest to understand the cosmos. Now, let's venture into one of the most mind-bending realms of modern physics: quantum entanglement. This strange phenomenon, often called spooky action at a distance, describes how particles can become linked in such a way that the state of one instantly influences the other, no matter how far apart they are. It's a concept that defies our everyday intuition, but when it comes to black holes, entanglement might hold the key to some of their deepest mysteries. Could entangled particles be the secret to understanding how black holes store and transmit information? And could this bizarre quantum connection even hint at the existence of wormholes? Let's unravel this cosmic puzzle. At the heart of this exploration is the ER=EPR conjecture, a groundbreaking idea that connects two seemingly unrelated concepts: entanglement and wormholes. The refers to Einstein and Rosen's work on wormholes, those hypothetical tunnels through spacetime we've touched on earlier. The EPR stands for Einstein, Podolsky, and Rosen, who first described quantum entanglement. The conjecture suggests that these two ideas are not just related, they might be two sides of the same coin. In other words, entangled particles could be connected by microscopic wormholes, creating a bridge between them through the fabric of spacetime. It's a concept that blurs the line between quantum mechanics and general relativity, two frameworks that have long resisted unification. But how does this relate to black holes? Imagine two particles falling into a black hole. According to the ER=EPR conjecture, these particles could remain entangled even as they cross the event horizon, their connection maintained by a wormhole-like structure. This entanglement could encode information about the particles, preserving it in a way that avoids the information paradox we've discussed earlier. In this view, black holes aren't just cosmic vacuums, they're vast networks of entangled connections, with each particle linked to others through a web of spacetime tunnels. It's a radical idea, but one that could explain how black holes manage to store and process information without violating the laws of quantum mechanics. What's even more fascinating is how this might tie into black hole shadows. The entangled particles near the event horizon could influence the way light behaves as it bends around the black hole, creating the intricate patterns we observe in their shadows. These patterns might not just be random, they could be a kind of quantum fingerprint encoding information about the black hole's structure and the entangled particles within it. If we can decode these patterns, we might uncover a new way to understand black holes, not just as gravitational giants, but as quantum systems with deep, hidden connections. The implications of this idea are staggering. If entanglement and wormholes are truly linked, it could mean that spacetime itself is built from a network of quantum connections. Black holes, with their extreme gravitational fields and intricate shadows, might be the ultimate laboratories for testing this theory. And as we continue to explore the quantum realm, we're left with a tantalizing question. Could entanglement be the glue that holds the universe together, weaving spacetime into a tapestry of interconnected threads? As we delve into the mysteries of quantum entanglement and its role in black holes, we're reminded that the universe is far stranger and more interconnected than we ever imagined. The shadows cast by black holes might not just be voids of darkness, they could be windows into a quantum reality where particles whisper secrets through the fabric of spacetime itself. And with each new discovery, we're not just uncovering the mysteries of black holes, we're glimpsing the hidden language of the cosmos. What if our universe isn't the only one? What if black holes, those enigmatic giants we've been exploring, are more than just cosmic vacuums? What if they're gateways to entirely different universes? This idea isn't just the stuff of science fiction. It's a serious scientific theory rooted in some of the most cutting-edge physics of our time. Welcome to the multiverse, a mind-bending concept that suggests our universe might be just one of countless others, and black holes could be the bridges connecting them. To understand how black holes might fit into this picture, let's take a closer look at one of the leading theories of brain cosmology. In this framework, our universe is thought to exist on a three-dimensional brain or membrane floating in a higher dimensional space. Other brains, other universes could exist alongside ours, separated by these extra dimensions. Black holes, with their immense gravitational pull, might be able to warp space-time so dramatically that they create tunnels or wormholes linking our brain to others. It's like poking a hole through a sheet of paper, a shortcut between 2 points that would otherwise be unreachable. But how would this work in practice? Imagine a black hole singularity, the point where the laws of physics break down. In the context of brain cosmology, this singularity might not be a dead end. Instead, it could be a portal, a kind of cosmic doorway leading to another universe. The intense gravitational forces near the singularity could distort space-time so severely that it connects our brain to another, creating a pathway between universes. It's a tantalizing idea, one that suggests black holes aren't just the end of a cosmic story. They could be the beginning of a new one. Of course, this raises a host of questions. If black holes are gateways to other universes, what would those universes look like? Would they follow the same physical laws as ours, or would they be entirely alien? And perhaps most intriguingly, could we ever travel through a black hole to reach them? While the idea is captivating, the practical challenges are immense. The extreme conditions near a black hole singularity would make any attempt at travel incredibly dangerous, if not impossible. But even if we can't journey through a black hole ourselves, the idea that they might connect us to other realities opens up a world of possibilities for understanding the cosmos. What's truly fascinating is how this ties into the multiverse as a whole. If black holes are indeed bridges to other universes, they could be part of a vast, interconnected network, a cosmic web of brains and wormholes, each universe linked to others through these gravitational giants. This idea not only redefines our understanding of black holes, but also reshapes how we think about the universe itself. Instead of a single, isolated cosmos, we might be part of a sprawling multiverse, with black holes serving as the threads that weave it all together. So, are black holes the gateways to parallel realities, or is this just a fascinating theory waiting to be proven? The answer, much like the multiverse itself, remains shrouded in mystery. But as we continue to explore these ideas, we're reminded that black holes aren't just the universe's most enigmatic objects, they're also its most profound storytellers. Whether they're bridges to other worlds or simply cosmic curiosities, they challenge us to dream bigger, to question deeper, and to imagine a universe or multiverse far stranger and more interconnected than we ever thought possible. As we ponder the possibility of black holes as gateways to the multiverse, we're left with a question that echoes through the cosmos. What other secrets might these gravitational giants hold, and how will they reshape our understanding of reality? The answer lies somewhere in the shadows, waiting to be uncovered by the curious minds of scientists and perhaps by the dreamers who dare to imagine the impossible. Dark matter is one of the most elusive and mysterious substances in the universe, making up about 85% of all matter, yet remaining invisible to our telescopes. It doesn't emit, absorb, or reflect light, but its presence is felt through its gravitational effects on galaxies and cosmic structures. Now, imagine this invisible force interacting with the most enigmatic objects in the cosmos, black holes. Could dark matter play a role in shaping these gravitational giants? And could black holes, in turn, help us unravel the secrets of dark matter, let's dive into this cosmic detective story. One of the most intriguing theories suggests that dark matter might influence the formation and growth of black holes. In the early universe, vast clouds of dark matter could have collapsed under their own gravity, forming dense regions that served as the seeds for black holes. These dark matter halos, as they're called, might have attracted regular matter, creating the conditions for black holes to form and grow over billions of years. In this scenario, dark matter isn't just a passive bystander, it's an active participant in the birth and evolution of black holes. But how exactly does this interaction work, and what does it mean for our understanding of the cosmos? As black holes grow, they continue to interact with their dark matter surroundings. Some theories propose that dark matter particles could accumulate near a black hole's event horizon, creating a dense spike of invisible matter. This spike could alter the black hole's gravitational field, influencing how it interacts with nearby stars and gas. In extreme cases, dark matter could even contribute to the black hole's mass, accelerating its growth and shaping its behavior. It's a subtle dance between the seen and the unseen, with dark matter quietly pulling the strings behind the scenes. But the connection between dark matter and black holes goes even deeper. Black holes might hold the key to detecting dark matter indirectly. When dark matter particles collide near a black hole, they could annihilate each other, producing bursts of gamma rays or other high-energy radiation. These emissions could serve as cosmic fingerprints, revealing the presence of dark matter in regions where it would otherwise remain hidden. By studying these signals, scientists hope to piece together the properties of dark matter, using black holes as cosmic laboratories to probe the invisible universe. And what about black hole shadows? The interplay between dark matter and black holes could leave subtle imprints on these shadows, altering the way light bends around the event horizon. If dark matter accumulates in specific patterns near a black hole, it could distort the shadow in ways that reveal its presence. This opens up the possibility of using black hole shadows as a tool to study dark matter, turning these enigmatic silhouettes into cosmic maps of the invisible universe. As we explore the relationship between dark matter and black holes, we're reminded that the universe is far more interconnected than it appears. What we can't see might be just as important as what we can, and black holes, with their immense gravitational pull, could be the key to bridging the gap between the visible and the invisible. And as we peer into their shadows, we might just find that dark matter isn't just shaping black holes, it's shaping our understanding of the cosmos itself. So, does dark matter hold the key to unlocking the mysteries of black holes, or is it simply another piece of the cosmic puzzle? The answer lies somewhere in the interplay between light and shadow, waiting to be discovered by those who dare to look beyond the visible universe. And with each new discovery, we're not just uncovering the secrets of black holes, we're revealing the hidden forces that shape the universe as a whole. Black holes are often cast as cosmic destroyers, but their true legacy might be far more constructive. Far from being mere voids in space, these gravitational giants have played a pivotal role in shaping the universe as we know it. From the birth of galaxies to the formation of stars and planets, black holes have been the silent architects of cosmic evolution, weaving the tapestry of the cosmos over billions of years. Let's explore how these enigmatic objects have left their mark on the universe, and what their influence might mean for the future. The story begins with the early universe, a hot, dense soup of particles and energy. As the cosmos expanded and cooled, gravity began to pull matter together, forming the first stars and galaxies. But black holes, particularly supermassive ones, were already at work behind the scenes. These colossal objects, which can weigh millions or even billions of times the mass of our Sun, likely formed soon after the Big Bang, growing rapidly by devouring gas, dust, and even other black holes. Their immense gravitational pull acted as cosmic anchors, drawing in surrounding matter and providing the gravitational scaffolding for galaxies to form. Without black holes, the universe might have remained a formless expanse of gas and dust, devoid of the intricate structures we see today. As galaxies took shape, black holes continued to shape their evolution. Supermassive black holes, often found at the centers of galaxies, played a dual role as both creators and regulators. On one hand, their powerful gravitational fields helped to bind galaxies together, ensuring they remained cohesive over billions of years. On the other hand, their energetic outbursts, powered by the infall of gas and dust, could heat up surrounding material, preventing it from collapsing into new stars. This delicate balance between creation and suppression has shaped the growth and development of galaxies, influencing everything from their size to their star formation rates. But black holes didn't just shape galaxies, they also played a key role in the birth of stars and planets. When a black hole feeds on surrounding material, it doesn't just consume, it also releases energy in the form of jets and radiation. These jets can travel vast distances, compressing gas clouds and triggering the formation of new stars. In this way, black holes act as cosmic matchmakers, bringing together the raw materials needed for star formation and setting the stage for the birth of planetary systems like our own. Without black holes, the universe might lack the rich diversity of stars and planets that make it so vibrant and full of life. And then there's the broader role black holes play in the cosmic web, the large-scale structure of the universe. The gravitational pull of black holes, combined with their influence on dark matter, has helped to shape the distribution of galaxies across the cosmos. They've acted as cosmic nodes, drawing galaxies together into clusters and superclusters, and creating the intricate filamentary structures that define the universe on the grandest scales. In this sense, black holes are not just local phenomena, they're global players, shaping the universe from the smallest scales to the largest. Looking to the future, black holes will continue to play a crucial role in the evolution of the cosmos. As galaxies collide and merge, their central black holes will come together, creating even more massive objects that will shape the next generation of stars and planets. Some black holes will continue to grow, devouring everything in their path, while others will slowly fade away through Hawking radiation. But their legacy will endure, etched into the fabric of the universe they helped to create. So, as we reflect on the role of black holes in cosmic evolution, we're left with a question that stretches far beyond the present. How will these gravitational giants shape the future of the universe? Will they continue to drive the formation of new stars and galaxies, or will their influence wane as the cosmos expands and cools? The answer lies somewhere in the interplay of gravity, time, and the ever-evolving universe, a story that black holes are still helping to write. And as we continue to explore their mysteries, we're reminded that these enigmatic objects are more than just shadows in the cosmos. They're the architects of reality itself. What if some of the universe's oldest black holes have been hiding in plain sight since the dawn of time? Enter primordial black holes, hypothetical objects that might have formed in the earliest moments of the cosmos, long before the first stars and galaxies came into existence. Unlike the black holes we're familiar with, which are born from the collapse of massive stars, primordial black holes could have sprung into being from the extreme conditions of the infant universe. These ancient relics might be tiny, no larger than an atom or as massive as a star, and they could hold the key to solving some of the biggest mysteries in modern astrophysics. The idea of primordial black holes dates back to the 1970s, when physicists first speculated that they could have formed in the chaotic soup of the early universe. As the cosmos expanded and cooled, regions of higher density might have collapsed under their own gravity, creating black holes without the need for stars. These objects would be like cosmic fossils, remnants of a time when the universe was a hot, dense sea of particles and energy. But why does this matter? Because primordial black holes could be more than just relics. They might be the missing piece in our understanding of dark matter. Dark matter, that invisible substance that makes up most of the matter in the universe, has eluded detection for decades. We know it's there because of its gravitational effects, but we've never directly observed it. Primordial black holes could be a natural candidate for dark matter. If they exist in large numbers, their combined gravitational pull could explain the mysterious forces that shape galaxies and galaxy clusters. Some theories even suggest that these ancient black holes could have seeded the formation of the first stars and galaxies, acting as the gravitational anchors that drew matter together in the early universe. But how would we find something so small and potentially so old? One clue lies in their gravitational effects. Primordial black holes, even the tiniest ones, would distort the light from distant stars as they pass in front of them, a phenomenon known as microlensing. By searching for these fleeting distortions, astronomers hope to catch a glimpse of these elusive objects. Another possibility is that primordial black holes could collide, producing ripples in space-time known as gravitational waves. Detecting these waves could provide indirect evidence of their existence, offering a new window into the universe's earliest moments. The mystery of primordial black holes isn't just about their origins, it's about their potential to reshape our understanding of the cosmos. If they exist, they could bridge the gap between the visible and the invisible, connecting the dots between dark matter, galaxy formation, and the early universe. And while we haven't found definitive proof of their existence yet, the search is far from over. With every new observation and every new theoretical breakthrough, we're inching closer to uncovering these ancient cosmic enigmas. So are primordial black holes the hidden architects of the universe, quietly shaping its evolution from the shadows? Or are they simply a fascinating idea waiting to be proven? The answer lies somewhere in the vast expanse of the cosmos, waiting to be discovered. And as we continue to explore, we're reminded that the universe's oldest secrets might be hiding in the most unexpected places, even in the tiniest, most ancient black holes. Black holes aren't just cosmic curiosities, they're also the ultimate laboratories for testing the boundaries of our understanding. At the heart of this exploration lies one of the greatest challenges in modern physics, the quest for a theory of quantum gravity. Quantum gravity aims to bridge the gap between two of science's most successful frameworks, quantum mechanics, which governs the behavior of particles at the smallest scales, and general relativity, which describes the large-scale structure of spacetime. And black holes, with their extreme gravitational fields and mysterious interiors, might just be the key to unlocking this elusive unification. One of the most promising approaches to quantum gravity is string theory. In this framework, the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings exist in higher dimensions, and their vibrations give rise to the particles and forces we observe. When applied to black holes, string theory offers fascinating insights. For instance, it suggests that the information swallowed by a black hole isn't lost but encoded in the vibrations of these strings on the event horizon. This idea aligns with the holographic principle, which we touched on earlier, hinting that black holes might store information in ways we're only beginning to understand. Another compelling approach is loop quantum gravity, which proposes that spacetime itself is made up of tiny, discrete loops. In this view, the fabric of the universe is like a woven tapestry, with each loop representing a fundamental unit of spacetime. When applied to black holes, loop quantum gravity suggests that singularities, those infinitely dense points at the center, might not exist as we imagine them. Instead, they could be replaced by a kind of quantum foam, a fluctuating region where space-time behaves in entirely new ways. This idea challenges the notion of a singularity as a place where physics breaks down, offering a potential resolution to some of the paradoxes black holes present. But why are black holes such a powerful testing ground for these theories? The answer lies in their unique combination of extreme conditions. Black holes are places where gravity becomes so intense that quantum effects can no longer be ignored. Near the event horizon, the interplay between gravity and quantum mechanics becomes impossible to separate, forcing us to confront the need for a unified theory. By studying how black holes behave in these extreme environments, scientists hope to find clues about how quantum gravity works, paving the way for a deeper understanding of the universe. As we explore these ideas, we're left with a tantalizing question. Could black holes hold the key to a theory of everything? A theory that unifies all the forces of nature and explains the fundamental workings of the cosmos. It's a lofty goal, but one that black holes bring within reach. Whether through string theory, loop quantum gravity, or another yet-to-be-discovered framework, these cosmic enigmas are guiding us toward a deeper understanding of reality. And as we continue to probe their mysteries, we're reminded that black holes aren't just the universe's most extreme objects, they're also its greatest teachers, challenging us to rethink everything we thought we knew about space, time, and existence itself. Black holes have long been seen as cosmic devourers, consuming everything that crosses their path. But what if they're not just destroyers? What if they're also cosmic recyclers, playing a vital role in the universe's cycle of creation and destruction? Far from being endpoints, black holes might be the engines that drive the universe's ability to renew itself. Let's take a closer look at how these gravitational giants recycle matter and energy, shaping the cosmos in ways we're only beginning to understand. At the heart of this recycling process are the powerful jets and outflows that black holes produce. When a black hole feeds on surrounding gas and dust, it doesn't just swallow everything whole, it also releases enormous amounts of energy. Some of this energy is channeled into narrow, high-speed jets that shoot out from the black hole's poles, traveling at nearly the speed of light. These jets can extend for thousands of light years, carving through the surrounding gas and dust like cosmic blowtorches. But instead of just destroying, these jets can actually trigger new beginnings. As these jets plow through the interstellar medium, they compress the gas they encounter, creating dense regions that can collapse under their own gravity. This compression is the first step in the formation of new stars. In this way, black hole jets act as cosmic catalysts, turning the raw materials of the universe into the building blocks of stars and planets. It's a process that transforms destruction into creation, recycling the energy and matter consumed by black holes into the seeds of new life. But jets aren't the only way black holes contribute to cosmic recycling. Outflows, streams of gas and dust ejected from the vicinity of a black hole also play a crucial role. These outflows can carry heavy elements like carbon, oxygen, and iron, forged in the hearts of stars back into the surrounding galaxy. These elements are essential for the formation of planets and ultimately life. By spreading these materials across the cosmos, black holes help enrich the universe, ensuring that the products of stellar evolution are not lost but instead become part of the next generation of stars and planets. This recycling process isn't just limited to individual galaxies. On a larger scale, black holes can influence the evolution of entire galaxy clusters. The energy released by supermassive black holes can heat up the gas in these clusters, preventing it from collapsing into new stars. While this might seem counterintuitive, it actually helps regulate the growth of galaxies, ensuring that they don't burn through their fuel too quickly. In this way, black holes act as cosmic regulators, balancing creation and destruction on a grand scale. So, what does this mean for the universe as a whole? Black holes, far from being the endpoints of matter and energy, are integral to the cycle of cosmic recycling. They take in the old and the used, transforming it into something new and vibrant. Their jets and outflows not only shape the galaxies around them, but also contribute to the ongoing story of star formation and galactic evolution. In this sense, black holes are not just destroyers, they're the universe's ultimate recyclers, ensuring that nothing is ever truly lost, only transformed. As we explore the role of black holes in cosmic recycling, we're reminded that the universe is a place of constant renewal. From the smallest particles to the largest galaxies, everything is part of an intricate cycle of creation, destruction, and rebirth. And at the center of it all, black holes stand as both the architects and the custodians of this cosmic dance, shaping the universe in ways that are as profound as they are beautiful. What if black holes aren't just cosmic mysteries? What if they're also cosmic signposts, pointing the way to life beyond Earth? While black holes are often seen as harbingers of destruction, they might play a surprising role in the search for extraterrestrial life. From shaping the conditions for habitability to potentially serving as markers of advanced civilizations, these gravitational giants could hold clues to one of humanity's most profound questions: are we alone in the universe? Let's start with habitability. Black holes, particularly supermassive ones at the centers of galaxies, have a profound influence on their surroundings. Their immense gravitational pull can shape the orbits of stars and planets, creating stable regions where life-friendly conditions might arise. For example, in galaxies with active supermassive black holes, the energy released during feeding events can heat up gas and dust, preventing it from collapsing into new stars. This process might seem counterintuitive, but it actually helps create a stable environment by regulating star formation and reducing the likelihood of catastrophic supernova nearby. In quieter galaxies where black holes are less active, this stability could allow planets to develop over billions of years, providing the time needed for life to emerge and evolve. But black holes might also play a more direct role in making certain regions of the universe more habitable. The powerful jets and outflows they produce can carry heavy elements like carbon, oxygen, and nitrogen, essential building blocks for life, far across space. These elements, forged in the hearts of stars and scattered by black hole activity, could enrich the surrounding interstellar medium, seeding new star systems with the ingredients needed for planets and life. Without black holes, the universe might lack the chemical diversity necessary for complex life forms to develop. Now, let's take this idea a step further. Could black holes themselves be indicators of advanced alien civilizations? Some scientists have speculated that highly advanced civilizations, capable of harnessing vast amounts of energy, might use black holes as power sources. A supermassive black hole with its enormous gravitational energy could be the ultimate cosmic battery, providing the kind of energy required for interstellar travel or even the construction of megastructures. If such civilizations exist, their activity around black holes, whether through energy extraction or the creation of artificial structures, might leave detectable traces. Observing unusual patterns of light or energy around black holes could be a way to spot these civilizations, turning black holes into cosmic beacons for intelligent life. This idea ties into the concept of Dyson spheres, hypothetical megastructures that advanced civilizations might build to capture the energy of stars or black holes. While we've yet to detect such structures, the search for them is part of the broader effort to find signs of extraterrestrial intelligence. Black holes, with their immense energy output, could be prime candidates for such projects. If we ever detect unusual energy signatures or structures near a black hole, it might not just be a natural phenomenon, it could be evidence of a civilization far more advanced than our own. So, are black holes markers of alien intelligence, or are they simply cosmic phenomena that happen to create conditions ripe for life? The answer, like so much about black holes, remains shrouded in mystery. But as we continue to explore their role in the universe, we're reminded that these enigmatic objects might hold more than just gravitational secrets. They could be the key to unlocking the mysteries of life itself, both where it exists and how it might thrive in the vast expanse of the cosmos. As we ponder the possibility of life beyond Earth, black holes invite us to think bigger and dream bolder. They challenge us to see the universe not just as a collection of stars and galaxies, but as a living, evolving system where the seeds of life might be scattered far and wide. And in their shadows, we might just find the answers to one of humanity's oldest questions. Are we truly alone, or is the cosmos teeming with life waiting to be discovered? When we think about the fate of the universe, it's hard not to imagine black holes playing a starring role. After all, these gravitational giants have shaped galaxies, influenced star formation, and even recycled matter and energy across cosmic timescales. But could they also hold the key to how the universe itself ends? From the fiery collapse of a big crunch to the cold, silent expanse of heat death, black holes might be the silent architects of the cosmos' final chapter. One of the most dramatic theories about the universe's fate is the Big Crunch. In this scenario, the expansion of the universe, driven by dark energy, eventually slows and reverses. As galaxies draw closer together, their supermassive black holes would collide and merge, creating even more massive objects. Over time, these black holes would devour everything in their path, from stars to gas clouds, until the entire universe is consumed in a single, infinitely dense singularity. It's a cosmic collapse that echoes the birth of black holes themselves, but on a scale that's almost impossible to comprehend. The Big Crunch would mark the end of everything we know, with black holes serving as both the harbingers and the final resting place of all matter. But what if the universe doesn't collapse? What if it keeps expanding forever, growing colder and emptier with each passing eon? This is the scenario known as heat death, where the universe reaches a state of maximum entropy, a kind of cosmic equilibrium where energy is evenly distributed and no work can be done. In this cold, dark future, black holes would still play a crucial role. Over unimaginable timescales, black holes would slowly evaporate through Hawking radiation, releasing their energy back into the universe. But even this process would take trillions upon trillions of years, leaving the cosmos a vast, empty expanse where only the faintest remnants of black holes linger. Interestingly, these two scenarios aren't mutually exclusive. Some theories suggest that the universe could experience multiple cycles of expansion and contraction, with black holes acting as cosmic bookmarks between each iteration. In this cyclic model, black holes might survive the collapse of one universe and seed the formation of the next, creating a kind of cosmic recycling on the grandest scale. It's a poetic idea that even in the face of total destruction, black holes could be the seeds of rebirth, ensuring that the story of the universe never truly ends. What's truly fascinating is how black holes connect these theories to the fundamental laws of physics. Their behavior, whether they're devouring matter, merging with one another, or slowly evaporating, reflects the delicate balance between gravity, entropy, and the expansion of the universe. Studying black holes not only helps us understand how the universe works today, but also offers clues about how it might end. They're like cosmic time capsules, preserving the secrets of the universe's past, present, and future within their event horizons. As we contemplate the role of black holes in the universe's ultimate fate, we're left with a profound question. Are these gravitational giants the universe's final architects, or are they simply part of a larger, more intricate cosmic design? The answer lies somewhere in the interplay of gravity, time, and the ever-expanding cosmos, a story that black holes are still helping to write. And as we continue to explore their mysteries, we're reminded that these enigmatic objects are more than just shadows in the cosmos. They're the keepers of the universe's deepest secrets, guiding us toward a deeper understanding of existence itself. So, whether the universe ends in a fiery collapse or a cold, silent fade, black holes will be there, shaping its final moments and challenging us to rethink everything we thought we knew about the cosmos. In their shadows, we might just find the answers to the universe's most profound questions and perhaps a glimpse of what lies beyond the end of time. Black holes have long been more than just scientific curiosities. They've become powerful symbols in art, literature, and film, capturing our collective imagination in ways that transcend their physical reality. These cosmic enigmas, with their unfathomable depths and mysterious nature, have inspired creators across mediums to explore themes of the unknown, transformation, and the infinite. From the haunting beauty of visual art to the mind-bending narratives of science fiction, black holes have become a canvas for humanity's deepest questions and wildest dreams. In the realm of visual art, black holes are often depicted as swirling voids, their event horizons glowing with otherworldly light. Artists like NAS, a visualization team, have used scientific data to create stunning, realistic portrayals of these cosmic giants, while others take a more abstract approach, using black holes as metaphors for existential themes. For instance, the works of contemporary artists like Olafur Eliasson or Anish Kapoor often evoke the sense of infinite depth and mystery that black holes represent, drawing viewers into a contemplation of the vast, unknowable universe. These artistic interpretations remind us that black holes aren't just scientific phenomena, they are also gateways to the human experience of awe and wonder. Literature, too, has embraced black holes as symbols of the unknown. In novels like Arthur C. Clarke's 2001, A Space Odyssey, or Liu Cixin's The Three-Body Problem, black holes serve as plot devices that push characters and readers to confront the limits of human understanding. They're often portrayed as portals to other dimensions or timelines, embodying the tension between fear and curiosity that defines our relationship with the cosmos. Even in poetry, black holes appear as metaphors for emotional voids or transformative journeys, their gravitational pull reflecting the forces that shape our inner lives. Film and television have arguably done the most to cement black holes in popular culture. Christopher Nolan's Interstellar brought black holes to life with scientific accuracy and artistic flair, using the black hole gargantua as both a narrative device and a visual spectacle. The film's portrayal of time dilation near the event horizon and its depiction of a higher dimensional tesseract inside the black hole sparked conversations not just about science, but about love, sacrifice, and the human spirit. Similarly, Event Horizon and Star Trek have used black holes as backdrops for stories of exploration and existential dread, showcasing their dual role as both physical and symbolic thresholds. But why do black holes resonate so deeply with us? Perhaps it's their duality. They're both destructive and generative, swallowing light while also inspiring creativity. They embody the unknown, the infinite, and the transformative, making them perfect metaphors for our own journeys through life. Whether we're gazing at a painting, reading a novel, or watching a film, black holes invite us to confront the limits of our understanding and imagine what lies beyond. As we reflect on the cultural impact of black holes, a question lingers: how will they continue to shape our stories and our art in the future? Will they remain symbols of mystery and transformation, or will new scientific discoveries change the way we see them? Whatever the answer, one thing is certain: black holes will always be more than just cosmic phenomena. They're mirrors reflecting our deepest fears, our boldest dreams, and our endless curiosity about the universe. And as long as we keep looking to the stars, they'll remain a source of inspiration, reminding us that the unknown is not something to fear, but something to explore. The study of black holes isn't just about unraveling cosmic mysteries, it's also a testament to the power of collaboration. These enigmatic objects have a unique way of bringing people together, uniting scientists from diverse fields and nations in a shared quest for knowledge. From astrophysicists and mathematicians to engineers and computer scientists, the exploration of black holes has become a global endeavor, showcasing how teamwork can push the boundaries of what we thought was possible. And nowhere is this spirit of collaboration more evident than in the groundbreaking work of the Event Horizon Telescope. The Event Horizon Telescope, or EIT, is a marvel of modern science, not just for what it has achieved, but for how it has achieved it. Imagine a telescope so large that it spans the entire globe, combining the power of radio dishes from Antarctica to Hawaii, from Spain to Chile. This global network doesn't just observe black holes, it creates a virtual telescope the size of Earth itself, capable of capturing details that would be impossible for any single facility. But building and operating the EIT required more than just advanced technology. It demanded unprecedented levels of cooperation. Scientists, engineers, and technicians from over 60 institutions across 20 countries worked together, pooling their expertise to turn a bold vision into reality. What makes this collaboration so extraordinary is the diversity of skills and perspectives it brings to the table. Astrophysicists analyze the data, mathematicians develop the algorithms to process it, and engineers design the instruments to collect it. Even computer scientists play a crucial role, creating the software needed to stitch together the terabytes of data generated by the EIT. Each piece of the puzzle is essential, and it's only through this collective effort that we've been able to capture images like the iconic shadow of the black hole in Messier 87. It's a reminder that no single discipline or nation can unlock the secrets of the cosmos alone. It takes a village, or in this case, a global community. But the EIT is just one example of how black holes inspire collaboration. Around the world, researchers are working together to study everything from gravitational waves to Hawking radiation, sharing data, ideas, and resources in ways that transcend borders and disciplines. This spirit of cooperation isn't just about advancing science, it's about fostering a sense of shared purpose. In a world often divided by differences, the study of black holes reminds us of what we can achieve when we come together in pursuit of a common goal. As we look to the future, it's clear that collaboration will remain key to unlocking the mysteries of black holes. New projects like the next-generation gravitational wave detectors and space-based telescopes will require even greater levels of international cooperation. And as these efforts unfold, they'll continue to bring together minds from every corner of the globe, united by a single question: what lies beyond the event horizon? The answer, as always, will depend on our ability to work together, to share our knowledge, and to dream as one. So, while black holes may be solitary objects, their study is anything but. They've become a rallying point for humanity's collective curiosity, a reminder that the pursuit of knowledge knows no boundaries. And as we continue to explore their secrets, we're not just learning about the universe, we're learning about ourselves and the incredible things we can achieve when we reach for the stars together. The story of black holes is far from over. In fact, it's only just beginning. As we stand on the brink of a new era in astrophysics, cutting-edge technologies and ambitious missions are poised to revolutionize our understanding of these cosmic enigmas. From next-generation telescopes to groundbreaking experiments, the tools at our disposal are more powerful than ever, and they're about to take us deeper into the shadows than we've ever gone before. One of the most exciting developments on the horizon is the launch of the James Webb Space Telescope, or JWST. While it's best known for its ability to peer into the earliest moments of the universe, JWST also has the potential to shed new light on black holes. Its infrared capabilities will allow it to observe the regions around supermassive black holes in unprecedented detail, capturing the faint glow of gas and dust as it spirals into their event horizons. By studying these processes, scientists hope to uncover new insights into how black holes grow, how they influence their host galaxies, and even how they might have formed in the first place. But the James Webb Space Telescope is just the beginning. On the ground, the Extremely Large Telescope, or ELT, is set to become the world's largest optical telescope when it comes online later this decade. With a mirror nearly 40 meters in diameter, the ELT will have the resolution to observe black holes in distant galaxies with stunning clarity. It could help us map the intricate structures of black hole shadows, measure their spins with unprecedented precision, and even detect the faint echoes of stars being torn apart by their immense gravity. These observations will not only deepen our understanding of black holes, but also provide new tests for Einstein's theory of general relativity in the most extreme environments. Meanwhile, the field of gravitational wave astronomy is entering a new golden age. The LIGO and Virgo detectors, which made history with the first detection of gravitational waves in 2015, are being upgraded to become even more sensitive. Future detectors like the planned LISA mission, a space-based observatory set to launch in the 2030s, will open up entirely new avenues of exploration. LISA will be able to detect gravitational waves from supermassive black hole mergers, events so powerful they can shake the fabric of spacetime across billions of light years. By listening to these cosmic ripples, we'll gain a new perspective on how black holes form, merge, and shape the universe around them. And then there's the Event Horizon Telescope, the global collaboration that brought us the first image of a black hole shadow. The EHT is expanding its network, adding new telescopes to improve its resolution and sensitivity. Future observations could reveal the dynamics of black holes in real time, capturing how their shadows change as they feed on surrounding material or interact with other objects. These snapshots of black hole activity will provide a window into the complex interplay of gravity, light, and matter, offering clues about the fundamental laws that govern the cosmos. But perhaps the most tantalizing prospect lies in the realm of quantum gravity. As we've discussed, black holes are the ultimate testing grounds for theories that aim to unite quantum mechanics and general relativity. Upcoming experiments, like those using quantum computers to simulate black hole behavior, could provide new insights into how these theories might work in practice. By probing the quantum nature of black holes, we might finally uncover the secrets of their singularities, their event horizons, and the information they encode. So, what does the future hold for black hole research? The possibilities are as vast as the cosmos itself. With each new mission, each new observation, we're inching closer to answering some of the most profound questions in science. How do black holes form and evolve? What lies beyond the event horizon? And how do they shape the universe on the largest scales? These are the questions that drive us forward, pushing the boundaries of what we thought was possible. As we look to the future, one thing is clear. The study of black holes is not just about understanding these enigmatic objects, it's about understanding the universe itself. Each new discovery, each new breakthrough brings us closer to unraveling the mysteries of existence. And in the process, we're reminded that the cosmos is far stranger, more beautiful, and more interconnected than we ever imagined. The future of black hole research is bright, and it's waiting for us to take the next step. Black holes, with their unfathomable depths and mind-bending physics, are more than just cosmic phenomena, they're philosophical enigmas. They challenge us to rethink some of the most fundamental questions about reality, existence, and our place in the universe. What does it mean for something to exist if it can be swallowed by a black hole, never to return? How do we reconcile the fact that these objects, which defy our understanding of space and time, are an integral part of the cosmos? These aren't just scientific questions, they're deeply philosophical ones, inviting us to explore the boundaries of human thought. At the heart of this exploration is the nature of reality itself. Black holes force us to confront the limits of our knowledge, showing us that the universe is far stranger and more complex than we ever imagined. Take, for example, the event horizon, a boundary where time and space seem to behave in ways that defy our everyday experience. For an observer outside a black hole, time slows to a crawl as an object approaches the event horizon, appearing to freeze in place. Yet, for the object falling in, time passes normally and it crosses the horizon without noticing anything unusual. This paradox isn't just a quirk of physics, it's a profound challenge to our understanding of what reality is and how we perceive it. But black holes don't just challenge our ideas about space and time, they also push us to reconsider the nature of existence. When matter falls into a black hole, it's compressed into a singularity, a point of infinite density where the laws of physics break down. What does it mean for something to exist in such a state? Is the singularity truly a place of infinite density, or is it a sign that our current theories are incomplete? These questions resonate with age-old philosophical debates about the nature of being and the limits of human understanding. Black holes remind us that existence as we know it is just one piece of a much larger puzzle. Perhaps the most profound philosophical implication of black holes lies in their ability to inspire wonder and curiosity. They're cosmic mirrors, reflecting our deepest questions about the universe and our place within it. Are we alone in the cosmos? What lies beyond the boundaries of our understanding? These are questions that have driven human thought for millennia, and black holes bring them into sharp focus. They remind us that the universe is a place of infinite mystery, full of questions that may never have answers, but that the act of asking them is what makes us human. In the end, black holes are more than just scientific objects. They're symbols of the unknown. They challenge us to think beyond the limits of our current knowledge, to imagine new possibilities, and to embrace the uncertainty that comes with exploring the cosmos. They inspire us to ask deeper questions, not just about the universe, but about ourselves. And in doing so, they remind us that the journey of discovery is as important as the answers we seek. So, as we continue to explore the mysteries of black holes, let's not forget to pause and reflect on what they teach us about the nature of reality, the limits of our understanding, and the boundless curiosity that drives us forward. As we bring this journey through the shadowy realms of black holes to a close, it's worth taking a moment to reflect on what we've uncovered. These cosmic enigmas, once thought to be mere voids in space, have revealed themselves to be far more dynamic and mysterious than we ever imagined. From their event horizons to their singularities, black holes challenge our understanding of the universe, pushing the boundaries of science and sparking our deepest curiosities. They are not just destroyers of light and matter, they are creators, regulators, and storytellers, shaping the cosmos in ways we are only beginning to comprehend. We've explored how black holes cast their shadows, not as mere absences of light, but as intricate patterns that encode the secrets of their structure and behavior. These shadows, captured by the Event Horizon Telescope, have given us a tangible glimpse into the invisible, confirming Einstein's predictions and offering new clues about the nature of gravity and spacetime. We've delved into the possibility that black holes could be portals, gateways to other dimensions, or even other universes, inspiring both awe and debate among scientists and dreamers alike. And we've seen how these gravitational giants play a vital role in the life cycle of galaxies, recycling matter and energy to fuel the birth of stars and planets. But perhaps the most profound lesson black holes teach us is humility. They remind us that the universe is far stranger and more complex than our current theories can fully explain. The mysteries of their singularities, the paradoxes of their event horizons, and the whispers of quantum entanglement within their depths all point to questions that remain unanswered. These cosmic puzzles are not just scientific challenges, they are invitations to keep exploring, to keep questioning, and to keep dreaming. As the great physicist Stephen Hawking once said, "Look up at the stars and not down at your feet." Try to make sense of what you see and wonder about what makes the universe exist. Be curious. Black holes embody this spirit of curiosity, urging us to look beyond what we know and to embrace the unknown with wonder and determination. They are not just objects in space, they are symbols of humanity's unending quest for knowledge. So, as we conclude this exploration, I invite you to share your thoughts. What fascinates you most about black holes? What cosmic mysteries do you hope will unravel next? Let's keep the conversation going in the comments below. And if you've enjoyed this journey through the shadows and secrets of the cosmos, don't forget to subscribe for more adventures into the wonders of the universe. Together, let's keep looking up, asking questions, and uncovering the stories written in the stars. The universe is waiting, and its